Hi, I'm Jim Stock, Vice Provost for Climate and Sustainability at Harvard, and welcome to Harvard Voices on Climate Change. I'm an economist and director of the Salata Institute for Climate and Sustainability. This series takes the broad Harvard community on a virtual tour of the research done at Harvard on climate and sustainability. Each hour focuses on a different topic featuring one or two Harvard researchers. Today, we're going to take a look at the energy and climate footprint of computing, and importantly, what opportunities there are for reducing that footprint. Computing, and especially AI and data centers, have been front and center in the news. One of the few areas of bipartisan agreement is on the idea that the United States should be the leader in artificial intelligence. After decades of flat growth, AI and data centers are projected to drive demand for electricity up, on top of projected demand from electric vehicles and heat pumps. Today, we're going to learn about the world of sustainable computing, a broad term that encompasses power use by computers and the carbon footprint that goes into making chips and computer components. I will admit this is an area I personally don't know a lot about, but what I do know is this field is evolving in real time. Just this week, DeepSeek, a large large language model from China, made big news and caused a sharp drop in the price of NVIDIA, the advanced chip maker, when it was learned that DeepSeek required a lot less computing power to build than its competitors like ChatGPT. I'm sure our guests will have things to say about this and related topics. Today, we have Gage Hills and David Brooks with us. Both are on the faculty of Harvard's John A. Paulson School of Engineering and Applied Sciences. David Brooks is the Haley Family Professor of Computer Science and is an expert in computer architecture, AI, and sustainable computing. Gage Hills is Assistant Professor of Electrical Engineering and works on technology for high-performance, ultra-dense integrated circuits. Both have worked on projects on sustainable computing supported by the Salata Institute. We'll start with presentations, first David, then Gage, then turn to questions. I have some pre-submitted questions, but if you have questions as we go, please use the Q&A feature. So with that, let me turn this over to David.
Thanks, Jim. I will share my screen and get started on the presentation. So today, I'm going to talk about the area of sustainable computing, and Gage and I work together in this topic. So we're going to do this tag team where I'll do some introduction, and then Gage will get into more of the details on some of the work on the fabrication of computing and how that impacts sustainability. Let me start with one of the favorite plots that computer designers like to show, which is the number of transistors per chip as demonstrated by the developed computers that have been built over the last 50 years. And what we can see from this is that this is a log scale plot. So what we're seeing is a linear increase on a log scale plot, meaning this is growing exponentially. And this is what is commonly known as Moore's law, which is that the number of transistors available to chip designers doubles roughly every 2 years. And this has been going on for at least 50 years, actually even longer. And we've been able to design our computers and our systems to take advantage of this to great effect. What's a little bit less well known, but is equally powerful in the design of computers, is the fact that we get better transistors from each generation of design as well. So as the technology matures, the transistors get smaller. Because they're smaller, they end up using less energy every time we switch one of those transistors. And the way we build computers is by taking all these transistors and combining them together to do arithmetic operations, logical operations, store data, compute the data, and present those results. What we see with this plot is that we've had a similar huge amount of improvement in the energy per switch over the last almost 100 years, going back to the early 1940s. Pre-1995, the improvement was about 1.6x per year. And this was also very consistent and is supported by theory of the scaling and the geometry of the transistors as we shrink them. Around 1995, roughly when I was starting my PhD work in computer engineering, we had noticed that the improvements were slowing. So when we went from 1.6x a year to 1.3x per year. And what this suggests is that we actually have a power problem because we're increasing the number of transistors at a very fast rate, but the energy per switch is not improving quite as much, and so the power starts to go up. This then kicked off the field of energy efficient computing. In the late 1990s was when this area became a research area that a lot of people started to think about, because before you didn't really have to do anything. You were kind of getting this as an artifact of the technology, but now we needed to think about it explicitly. The other thing I've drawn on this plot is so-called Landauer's limit, which is a theoretical limit presented by physicists about how low the energy per switch can go. And what you can see is over the years, we've gotten closer and closer to that limit, and projections in the future are that the energy per switch is going to start slowing. We're just getting really, really close to what's possible to be done with the basic physics. As an engineer, this is extremely impressive that we're so close to a physical limit, but it's also a little bit scary because the entire computing industry is based on the two graphs I've just shown, Moore's law and these energy efficiency benefits. So what do we do about this? I mentioned that in the late 1990s, early 2000s, people started to take this seriously as a first order constraint as when we design our computer systems. Much of the research that has gone on in our lab and other labs has thought about this energy efficient computing as a way to extend the lifetime of the performance improvements we get, even if the energy per switch is going not increasing as we have in the past. And this is just a sort of example techniques. We're called computer architects in the technical field because we think about how to take those transistors and put them into blocks, and then take those blocks and build computing systems out of them. Not unlike the way that traditional architects take bricks and mortar and pestle and put together large buildings. And think about all the right ways to take those components and put them together for houses and offices and so forth. We can similarly make this analogy between the techniques that we're using to make energy efficient computers with what we see in the way we build our buildings. So for example, we'll often do an architectural design space analysis that thinks about, am I using a computer for a cell phone or a data center that's doing AI training? Those are very, very different scenarios, and we need to choose the right architecture for those scenarios. In the same sense that you need to choose the right house size for your needs. You don't want something too big for your needs because that's energy inefficient. Similarly, we have techniques that allow us to adjust the performance and energy of our computers at runtime. Things like changing the frequency and voltage, how fast your computer runs, and how hard we're pushing the transistors to run faster. The adjustments that we make are not unlike what you do with your home thermostat to try to reduce the energy costs and only use the amount of heating and cooling that you need for the conditions that you're in. Similarly, with this dynamic voltage and frequency control, we're able to control individual portions of a chip by applying different voltages, different parts of the chip, depending on their needs. This is, again, analogous to having zoned heating and cooling, where certain rooms you can have higher temperature where you're spending more time there, and other rooms you let them be cooler because it's less active. We have techniques called clock gating, and this is, again, not unlike turning on and off the lights in a house. So if you walk into a room, you want the lights to turn on. When you leave the room, you want them to turn off because you're no longer in there. With clock gating, what we do is we turn on and off parts of the chip dynamically, depending on whether we're using that part of the computer or not. There's a technique called heterogeneous big little. This sounds quite exotic, but what it is basically having one big, really fast chip sitting next to a small, more efficient chip. And again, this would be similar to having a two-car garage where you have an SUV parked next to your Prius, and you use the Prius to do your day-to-day shopping and going to work and whatnot, and then you use the SUV when you really need it because you're going off on a camping trip and you need to carry a lot of stuff there. With the heterogeneous big little, what we do is we'll use that big fast core when we really need performance, and then the rest of the time we'll try to get away with the little core. And as the human user, if we do a good job with this, you won't notice that you're switching between the little and the big core, and we'll save a lot of energy. Dynamic thermal management, inside chips, they get very hot, and we need to adjust the performance to those temperature scenarios. So we can slow down parts of the chip, we can turn off parts of the chip to mitigate these thermal hotspots. One of the biggest evolutions that we've seen in computer design over the last decade, and something that our lab has focused on quite a lot, is the evolution from the general purpose CPU era, where computers were designed to handle any task. They needed to be able to run PowerPoint, Word, web browsers, everything that you would want to do. And they had to do those tasks in a reasonably efficient way. But what was most important is that generality. And then as we've moved into what we call the specialization era, we now design computers that can do specific tasks. They'll do those tasks much better than a general purpose computer, but they'll only handle that task. So the classic example that we have now are computers that are designed for AI processing. And if you design a computer for AI processing, you can get 10, maybe 100x better compared to a general purpose processor, but you can't use that computer for anything except AI processing. So that's sort of the trade-off that we have. And as domains like AI, robotics, and so forth become more prevalent, the specialization era is really reaping benefits for energy efficiency. So where's all this got us? The combination of the technology scaling, the combination of all of these ideas in terms of energy efficiency, even the specialization knobs. It's actually quite interesting because on the past roughly 20 years since 2020, 2019, the total data center electricity consumption of the United States was roughly constant. We were growing things quite a lot. We were building a lot of data centers. We were adding more computers, but the energy efficiency benefits were canceling that out. And we had roughly constant power draw, around 2% of the total, which doesn't sound too bad. And certainly computing has improved the productivity of many other industries. What we've seen over the last 5 years is we've roughly doubled that. This is projections that were just made last month, that we're now about 4.4% towards the end of 2023, early 2024. And the two curves that you see here are the forward projections, assuming different rates of growth in the computing industry. So ranging from 6.7 to 12% by 2028. And the obvious answer for why this is the case is that AI has taken off in tremendous amounts across all areas of our industries. And so a few years ago, AI was something that we had, but it was a relatively small fraction. Now it's roughly 50% of the computers that we have in data centers are AI servers, and this is the part that's growing the most as we look ahead. So how do we address this? When we think about the technology companies that are out there, they have talked about this. They're aware of the problems. They're focused on carbon neutrality. There's a lot of pledges that are out there. Most of these towards the end of this decade, they want to be carbon neutral or carbon negative. It's challenging though, and this is where a lot of the research comes because as a technology company, there are really two sources of emissions that you have to focus on. If you look at the greenhouse gas protocol, there's so-called scope 1 emissions, which tend to be pretty small for technology companies. But the scope 2 emissions for the energy they buy are much higher. And the scope 3 emissions of purchasing the hardware and building the hardware tend to be quite high as well. Gage is going to focus on talking about this in the next section, as well as the scope 3 emissions of the products that they sell. So as we think about sustainable computing, there are really three tenets that our lab focuses on. We think about energy efficient software and hardware. I talked about some of the ideas that have been developed. Some of these came out of our labs, and they're now in a lot of the systems that you have today, phones, data center computers, and whatnot. With energy efficient software and hardware, we're pushing this further. We're trying to look at what we can do for AI computing in particular using edge-based chiplet technology. So taking chiplets and chiplets being small little fractions of a chip that would normally be monolithically connected, with chiplet technology, we can connect these in heterogeneous ways that are different from what you can do with past techniques. Pushing the bounds on sparsity, and in AI, there's a lot of sparse computation where you just have zeros or computation that's not needed to get to the end result. We can prune those out or find ways to use fewer bits in the computation to save significant amounts of energy. I've talked a lot about the technology focus of computer design with the number of transistors and the energy per transistor. we're constantly looking for what's next. We want to know what are the new technologies that are going to help us evolve. So 3D stacking, where you take chips and put them on top of each other, some of the stuff that Gage works on, or emerging memory technologies that have more energy efficiency at perhaps some other trade-offs. We're also very interested in carbon-free energy, exploiting the characteristics of AI workloads and the spatial and temporal flexibility of those workloads. AI training, for example, can be done anywhere, and it tends to be very dense. So there's a lot of flexibility in where you put those data centers, and can you put them in areas that have more carbon-free energy? Can we anticipate and exploit trends in the energy technologies, the types of technologies that are out there? Can we take advantage of those in order to tie the computation with the energy technology that we get? So for example, market mechanisms that allow us to dial down some of the computing and push it in back to the grid when there's less renewable energy is being generated, and conversely, use more energy when there are curtailments where there's too much solar or too much wind being generated. Data centers are flexible enough to be able to take that into account. And finally, extending the refresh cycles, reuse and recycle, the common tenets of environmental efficiency allow us to use different kinds of AI hardware in data centers. Instead of everything having to be the same type of hardware, if we are able to exploit GPUs that were designed 2 years ago, 4 years ago, as well as the current ones, we can train the larger models by harnessing the inherent heterogeneity that we have in these data centers. But that requires a lot of interesting research challenges to be addressed in terms of scheduling and how you put the pieces together. Extending the lifetime of our hardware is also quite useful. Being able to take a piece of hardware and use it for 6 years, 8 years, 10 years, instead of throwing things away after 2 or 3 years, would greatly increase the efficiency from a embodied carbon point of view. And in order to do that, we need to improve the reliability and availability of these systems. So this gives you a flavor for the kind of things that we do in our lab, both in terms of past techniques and the kind of things that we're looking at, particularly in the sustainable computing space. Just want to wrap things up by acknowledging a lot of the students, the PhD alumni from our group who have focused on these things. Many of the research threads have come together over the years through different aspects of the projects, starting with specialization and thinking about AI specialization, thinking about data centers, thinking about sustainability as a first-class metric, and finally, some of our current work on large-scale AI co-design, which I'm happy to answer more questions about in the future. Finally, acknowledging our sponsors, the Salata Institute and National Science Foundation, and one more graduate alumni, Benjamin Lee, who was the co-PI on our large NSF expedition on this topic. With that, I will close things out and turn the floor over to Gage.
All right. Thank you, David. I guess you guys can see my slides. All right. Yeah, so this is Ecosystem for Sustainable Computing, Part 2. So obviously following up on David's presentation, and it's nice that we have David to do a little bit of the motivation for the need for sustainability and sustainable computing, so I can sort of jump right into it. But I do want to say just a little bit about sort of who I am and give you kind of a sense for the stuff that we work on, in my group, and then with some of the students that we collaborate with David and Gu, and some of our other collaborations in this space at Harvard. So my background is a little closer to the physical hardware than David. So I would sort of identify as a circuit designer. So a lot of my research in the past is focused on basically what David was talking about, this energy efficient computing. And if you think about sort of what energy efficient computing means, which I've been thinking about a lot recently, is basically that you want to compute fast, right? We want all of our AI models to be able to run very quickly. We want to be able to train stuff quickly. We want to do quick inference. And we want to do that while consuming a small amount of energy. So that's what I think of as energy efficient computing. And in this talk, I'm going to sort of reference something I've also been thinking a lot is this sort of like what's next past energy efficient computing? Like what's the next sort of like resource we should be considering? Because energy doesn't really feel like the only thing that we need to think about anymore. It's also like this, carbon footprint of computing or just environmentally sustainable computing in general. Even thinking about things like the water usage to manufacture computer chips or the toxicity of computer chips and semiconductor manufacturing, going into our wastewater and stuff like that, like all sorts of stuff that's popping up that's making computing systems unsustainable. So yeah, so this talk I'll talk about this sort of evolution from energy efficient computing to carbon efficient computing. And you can think about carbon efficiency as a sort of placeholder for this just environmentally sustainable computing. Yeah, so in my group, we have 7 PhD students. This is my fourth year at Harvard. We work generally on these areas related to energy efficient computing. My background, sort of like what David was talking about, is in these developing new technologies for energy efficient computing. And this, like David was saying, we can't just rely on making the transistors smaller and smaller anymore. We're not getting the same kind of benefits that we used to. And so some of the things I'll talk about today is these sort of multifaceted approaches, combining like different types of materials, like different types of semiconductors, like not just silicon, there's other types of semiconductors we can use. Different types of devices, like some of the different types of memory technologies that David alluded to. And this last one, this sort of 3D integration, where we can actually take like multiple chips and sort of stack them directly on top of each other. Because it turns out that a lot of the performance bottlenecks in our computing systems today is basically just due to passing data back and forth between different chips. Like if you think about like a large data center that's might be training one of these large language models, these data centers might have like literally like hundreds of thousands of processing units that are spread across like a warehouse. And all those like chips are running like super fast, so like these gigahertz. But you have a huge bottleneck in just moving the data around. Because even like if you think about even if you can transmit data at the speed of light, like from one side of a data center to the other side of a data center, speed of light is actually not that fast. Don't quote me on that. But speed of light is about 1 cent. Let's see. It's like, I was just talking about this in class today. It's like 30 centimeters per nanosecond. So a nanosecond is actually not that fast in computing land because a gigahertz means you're computing something every nanosecond. And if you can only transmit data 30 centimeters, that's not that far. So that just time of flight to transmit data from one side of a data center to another side can be a very big performance bottleneck. And if you can get stuff like your integrated circuits physically as close as possible, like stacked on top of each other in 3 dimensions, that gives you a big benefit in terms of overall performance. So we also then work, I mentioned light. We work on some of these electronic plus photonic integrated circuits, where we have the sort of conventional circuits that we use for computing that use electrical transistors. But then to actually transmit data, we use light and fiber optic cables to send data around. And then this last thrust that I'll talk about today is in this sort of connecting these first 2 thrusts into this environmentally sustainable computing. So there's a student, Miriam, who probably most of the work that you'll see today is from her and Danielle. And then because there's been so much excitement in this area, like all my other students like want to work in this area as well. And of course, I'll mention the people that don't actually do the work, including myself, because it's all just the PhD students that are the ones that are actually doing the work. But yeah, these are some of our collaborators at Harvard. So Udit was actually the one that sort of introduced me to this sustainable computing at Harvard. He's now a professor at Cornell Tech. He was a PhD student in David and Gu's group. Gu has also been on some of the Salata funded projects that we've been working on. And then we have collaborators, Minlong Yu is in computer science, and then Carol Jean Wu at Meta has also been major contributor to a lot of this work. So yeah, so the need for sustainable computing, I don't need to get into this. Thanks for David for introducing and same with Jim. But I want to highlight something that was like really shocking to me as an energy efficient, someone who thinks that they're an energy efficient computer designer, that if you actually look at this is from a sustainability report in around 2020 for Apple's carbon emissions. I think this was for like a iPad 11 or something like that. That if you actually look at where the carbon footprint comes from, most of it comes from what we call this embodied carbon that David referred to, that just the carbon footprint of like physically manufacturing like all the hardware. And a lot of that, look, I mean, even like a third of this is from physically making the integrated circuit. And if you look at this operational carbon, it ends up only being like maybe like a fifth of the overall uh, contributor to the carbon footprint. So this operational carbon would come from the actual like energy consumption from like the day-to-day use of the hardware. And so as an energy efficient circuit designer, that's typically the energy that we're thinking about, right? The energy that's actually used, like when the computing chip is being used, as opposed to the energy that is required to manufacture the chip. And since, as David was alluding to, like this energy per switch for all of our transistors is getting so small, but at the same time, it's taking more and more energy to physically do the manufacturing. To do this, like you hear about these like 3 nanometer technology node or 2 nanometer technology node using these like extreme ultraviolet light sources, like very high energy photons, like a lot of energy is required to physically make these chips. And so this was very concerning to me because I had this feeling like, am I not even working on the problem if I'm just considering this operational energy or operational carbon? Like, am I really even looking at the right resource? And so I think this was sort of shocking to me, but at the same time, sort of exciting and inspiring because it feels like we're going through this like paradigm shift in how we design computing systems, where it's not just thinking about energy as our resource for energy efficient computing, where you might think of like, okay, how many joules of energy do I need to use in order to get my computer chip to run fast in hertz, gigahertz? To thinking about like, okay, how many emissions am I generating to get my computer chip to run fast? I think this is this transition from energy efficient computing to carbon efficient computing. So while this is exciting, this naturally brings on sort of like two questions. Probably more than that, but at least two that I've identified here is one is, will this really catch on? Like, will people actually do this? Will companies actually be incentivized to reduce their carbon footprint to improve computing? Will manufacturing facilities, like what sort of mechanisms can we do to like enforce these manufacturing facilities to reduce their carbon footprint? And even if we can do that, then like how do we like go through the day-to-day sort of design process of making carbon efficient computing systems? Because one of the problems is there's a lot of uncertainty in carbon accounting. If we want to optimize the carbon footprint of the computing chip that I'm designing, like I need to be able to have some model for what that carbon footprint is. And if a lot of that carbon footprint comes from the manufacturing, then as a designer, I need to have some insight into the manufacturing so that I can maybe say like, okay, well, I don't need this manufacturing step because that's only going to give me a small benefit in terms of my computer chip performance, but it might cost a lot of carbon. If I don't know that type of information, or if the companies aren't willing to provide that type of information to me as a designer, then I can't really do carbon efficient design. So there's a lot of this uncertainty in this carbon accounting, or people might be sort of like hiding maybe some of their carbon footprint. So without this sort of proper accounting mechanisms, this gets really hard. And that's sort of challenging, not just from like a technical physics kind of point of view that circuit designers typically work at, right? This is something where there might need to be some kind of like policy enforced for companies to actually report their carbon footprint. This second bullet is then related to this like embodied carbon, which I've been talking about. Is like, okay, well, yeah, we need to have actual models for what these, what's the carbon footprint going to be of manufacturing. Without that, it's basically impossible to do this carbon efficient design. So I'll sort of address this first question first with some of the points that David was bringing up, that I do think there is hope for this carbon efficient computing, because if you sort of look back historically, like David was saying, in this sort of glory days of transistor scaling with Moore's law, we could just not even have to worry about the power consumption or the energy consumption of the chip. It was just naturally getting better because the transistors were getting smaller, and we could do basically just optimize the chips for performance. And then, power basically became a problem. It got to the point where if we kept going along that path, the chips would generate so much heat that they literally would melt. And this is a problem that we actually have to specifically design around. And because this was sort of like this global problem with designing integrated circuits, like humanity sort of rose to the challenge, and this guy, sort of Bob Denard, I would call the sort of father of this energy efficient computing, came up with this roadmap for how we can actually continue to scale transistors in such a way that maintains that reduces their energy in such a way that the power density of the chip doesn't continue to doesn't sort of run away. And so this, I think, was an example of like there being a sort of global problem that people identified and rose to the challenge of developing an infrastructure to overcome it. And nowadays, we literally don't run our computer chips as fast as they can run because they would melt. And so what I'm showing here is a plot of like a bunch of different computer chip designs. These are like varying some of the design knobs that David was talking about, with like this dynamic voltage and frequency scaling, like the supply voltage, a clock frequency. And you can sort of trace out this curve of like how much energy the chip is consuming as a function of how fast it's running. And so even though the chip can maybe run up here at this very farthest point on the right at maybe 5 or 6 gigahertz, we choose to operate it at a much more energy efficient point, that's circled here in yellow, because that offers a much better trade-off in terms of energy and performance. And I think that this same kind of thing, what I envision that in the future, like people are going to look back on what we're doing now and think that it was like absurd that that we are currently designing chips without thinking about their environmental impact or their sustainability. Just the same way that we look back like 30 or 40 years and think of it as just being crazy that people used to design chips without thinking about the power consumption. So yeah, I mean, I really think that this is sort of the next step in computing, this evolution from energy efficient to carbon efficient and environmentally sustainable computing. Of course, there's challenges with this, and the one that I'll sort of spend the rest of the time talking about is related to this embodied carbon, because this is also a project that Jim had mentioned that we've worked on with funding from Salata, basically looking at how we can come up with predictive models for this embodied carbon, the sort of energy consumption required to physically create these computing systems, that would help designers actually design them in a much more sustainable way. So I'll break this down. I won't spend much time talking about this operational carbon because this is relatively easy for us to model, because of this sort of ecosystem for energy efficient computing that Bob Denard sort of was the father of, I would say. We all of our tools and design infrastructure for creating integrated circuits gives like ridiculously accurate models of how much power and energy a chip is going to consume. Like we can model like at every nanosecond or every picosecond, like how much power is going to be flowing through the chip as a function of the state of all the transistors. And then because we have that model of the energy, then we can use information from like various power grids that tell us this sort of carbon intensity, which is a relationship between the energy consumption and then how much the sort of equivalent carbon footprint is in like equivalent grams of CO2. This embodied carbon, on the other hand, like I said, is much more challenging because this requires information about the fabrication process. So there is sort of good news and bad news here. The good news is that people are starting to recognize that this is a problem, and there are models being developed that designers can use that actually describe and give quantitative numbers for at a very fine-grained scale for fabricating every single layer of a computer, of an integrated circuit. And I'll show you some actual cross sections of an integrated circuit in a few slides. The challenge with this is that most of these models are based on technologies that already exist today. So chips that have like basically been already have been made, that the infrastructure has already been developed within the last like 5 to 10 years, and that infrastructure is not going to change. But like David was saying, in our research group, we're very interested in what's like the next thing that's going to be coming down the pipeline, right? Like we should be looking at what are the future directions in computing. And in order to, and we do this all the time for energy efficient computing. There's all sorts of research looking at the different potential options for, I mentioned these kind of 3-dimensional integrated circuits or different types of materials. All the time we do predictive analysis, like, okay, and if you could do this type of technology in 10 or 20 years, these are what the benefits would be. And that can help guide the directions that we pursue in energy efficient computing, right? Like, oh, even if we were to develop this, technology A, it's only going to give us like a 5% benefit. But if we develop technology B, that gives us like a 4x benefit. So let's invest all of our resources there. And that's what we think that we should be doing for this carbon efficient computing also, right? We need to be able to do this predictive modeling of carbon efficient systems. And to just give a sense of what these sort of 3-dimensional or future technologies look like, this is sort of illustrating what I was talking about earlier, that there's a major performance bottleneck in just transferring data around in a large-scale data center. So you can imagine this graphic of, of these sort of 4 different computing chips, and these things on the outside are like memories. Imagine this, but like even at a much larger scale, like hundreds of thousands of these in a data center. And these sort of links between them are the major performance bottlenecks in terms of communication. And so if you can actually build these, this is actually like a cross section, like a zoomed in view, like maybe like 1 million or 1 billion times of a 3-dimensional integrated circuit, where you like on these different circuit layers, you have different layers of transistors. These red and green and blue things are all the tiny little wires and transistors that are actually performing the computing. And by integrating everything directly on top of each other, then you get these distances to be very, very small, like on the order of like nanometers or microns, where that data communication can be much faster. And so people have done a lot of research in looking at the energy efficiency benefits of these types of 3-dimensional systems, but there is very little known about the embodied carbon footprint of making these. Because you can imagine that physically making this type of chip would have a much higher cost in terms of its embodied carbon, just to physically fabricate all of these layers on top of each other. These are just insanely complicated processes that involve like hundreds of steps, like different layers of metals and oxides and semiconductors that you're integrating on top of each other, that take like literally months to do. And these are just very intensive processes. And so our approach with this is that we want to basically develop these models that allow us to do this predictive analysis of how to manufacture these 3D computing systems. Because we think that can really guide the development of these technologies, like before all the infrastructure is being set up to manufacture them. And that's basically was this was the seed funding that we got from Salata, was for this project in particular, is quantifying the embodied footprint of these future computing systems. And I hope that sort of makes a little more sense to you now, than it would have if I had said that maybe 30 minutes ago. But yeah, so this was a great seed funding project. This was very successful. We have published like 2 papers out of this. We're going to be presenting these in Vegas in the beginning of March, and then we're going to be presenting the other one in France at the end of March. And then this has also led to like a lot of external funding, additionally from National Science Foundation, that has come out. I think this sort of approach of being able to predictively model the embodied carbon for these future computing systems is really resonating with people, because they realize the importance of doing this for energy efficient computing. And so we should, of course, do this for carbon efficient computing as well. And I realize I am probably rambling, but I'll just wrap up. I want to show you some of these cross sections of some of these chips and just give you a sense of how we actually develop these models. So this is actually like, if you imagine that 3D chip that I showed before, this is like, imagine you slice through that thing and look at it like you sliced a cake, and you're looking at, like, slice a wedding cake and you're looking at all the layers, as a cross section. So on the left is the type of chips that we typically make today, where the whole width of this thing is probably about 40 or 50 nanometers for scale. So just tiny. This is a single transistor on the bottom made out of silicon. And then there's all these layers of metal. These M1, M2, M3 is like metal 1, metal 2, third layer of metal. And these vias are these tiny little pieces of metal that connect them. And so when we do this manufacturing, this is what we're physically creating. And then these 3-dimensional chips, the challenge is that they need these sort of much more exotic types of transistors to put these transistors like up in these upper layers of the chip. It's very challenging to make our sort of conventional silicon transistors like up in these layers, because it takes a very high temperature processing to make these silicon transistors, like somewhere around like 1,000 degrees Celsius. So if you try to make another layer of silicon like up on the top and then bake it up to that really high temperature, you'll like literally just melt everything that you already made. And so you have to use these different types of transistors. This is a carbon nanotube field effect transistor. You use a different type of semiconductor. This IGZO is another type of semiconductor. Is indium, gallium, zinc oxide, some weird combination of materials that also gives you a transistor. And these ones you can make at low processing temperatures and create these 3D circuits. So the challenge is like, okay, well, nobody really makes these types of 3D circuits, so it's very hard to come up with these embodied carbon models. But the sort of key insight, and I would like not even really call it an insight, because it actually turns out to be relatively simple, is it to make these like 3-dimensional integrated circuits, you're really just using the same process steps like in a different order. Like up here is all still just like metals and oxides and semiconductors. And so you're just doing more of the same process. And it's like making like a 4-layer wedding cake instead of like a 1 or 2-layer wedding cake. You're still using like just all the batter and frosting and baking stuff. And so if you can break that down into the sort of energy required for every single one of those individual steps, you can very easily come up with a model for making sort of any arbitrary cake or any arbitrary integrated circuit. And that's basically what we have done is sort of taking these processes like step by step, and I'll just sort of leaf through these and look at, for every single step in this process to make these kind of chips, basically break that down into a fine-grained model of the energy consumption. And from that, then we can get basically the carbon footprint of the manufacturing. And so now we have a model for being able to model this embodied carbon of these future computing systems that don't even exist yet. And we can combine these within our models for the power, performance, area, and cost, and come up with this sort of holistic framework that allows us to sort of, in a very holistic sense, like evaluate, okay, if we were to make these, technology A versus B versus C, like what is its benefit in terms of power, performance, and area, and what's its benefit in terms of embodied carbon. Maybe one technology gives you sort of, maybe a 10x benefit in its performance, but comes with like a 20x cost in the carbon footprint. There might be another technology that gives you less performance, but is much lower in terms of its carbon footprint. And yeah, then you can sort of use this to do this optimization that David was alluding to with this hardware refresh. How often do you want to refabricate these chips? When do you want to switch to the new technology node? When do you want to swap in? Upgrade and use the latest and greatest technology and pay the cost for that embodied carbon. With this sort of holistic modeling framework, we can answer those questions very concretely. I think I'm not sure if these slides are shared or not, but there's some links to some of our additional work here. Obviously, want to say a big thanks to Salata for helping to fund this project. It's really been like I think the perfect outcome for a seed funding proposal. Also, fellowships for the students, and we have a bunch of support from National Science Foundation on this also. So yeah, with that, I'll wrap it up finally and turn it over for any questions.
Okay, great. So that's, boy, there's a lot of material here to talk about, and I'm really thrilled and pleased that you both took the effort to prepare such detailed presentations. You know what I'm going to do, we only have maybe 15 minutes left or a little less than that. So I'm going to actually go straight to some of the questions in the audience. Because there's a number of pretty interesting ones, and also some of the questions that were submitted in advance. So one question that came up, and I think you might have answered this in the speed of light thing, but I'd love to get an explanation. One question that came up from the audience is about, can you just locate these data centers? If we think about not what you've been talking about, which is the embodied carbon, but the operational side, can you just locate the data centers in such a way that they're using clean energy? Now, I know that, you could put, like, can you put them all in Arizona, or can you put them all in Norway, where it's essentially all hydropower? And now my guess is you're going to say, and then that's related, like, why in the world are they all actually in Northern Virginia? And you're going to have to explain the word latency, I think, in the answer to this question.
Yeah, there's a lot of trade-offs in the choice and site selection process for data centers. Energy supply certainly being a major one, but there are other things. With Northern Virginia has this confluence of fiber optic cables that have been put there for many, many reasons, and data centers do need to be physically proximate to their users. Now, when you're doing AI training, it's less of a concern because it's sort of number crunching off in the background while you're doing these massive experiments. So those might have more geographical flexibility and could be put in places that have more renewable energy or are more amenable to the environmental challenges.
Yeah, so there's that, and I would also say, there's sort of two components to this. One is the sort of physical location of the data center and the latency associated with, getting data from, your home or wherever you're querying that, like, to the data center. But even within the data center itself, right? If you want to be training a model, like, you have a huge room or warehouse of these chips that all have to talk to each other to do the training. And even like speed of light from one side of the room to the other, it ends up being a bottleneck because the chips themselves are so fast that they can just crunch all their data before even sending the data to the other side of the room. And so that's like a sort of totally different challenge. That's just more related to even the speed as opposed to the energy or carbon footprint.
You'll have to keep the answer to this short, because maybe I'm the only person who is interested in this. This Landauer's law, which I wasn't aware of, seems really important. Is that something that's specific to silicon chips? Does that apply to your carbon nanotube chips? Does it apply to quantum computing?
Gage, do you want to answer it?
Yeah, so I would say that there is some sort of fundamental idea of like the energy required to like change the state of something, like whether that is the state of like an electron on a gate. Like in order to compute something, like you're by definition sort of changing something,
I
like
see.
however you're representing that information. A photon over here, or a photon over here, or the state of a memory cell or something, and there's some fundamental amount of energy that's required to
So this really comes from the fundamentals of quantum computing, and excuse me, quantum mechanics and
yeah,
information theory.
right.
Okay, great. That's super helpful. Question in the from the audience. Several hyperscaler companies have investigated integrating direct air capture with data centers. The idea is to take advantage of waste heat, because most forms of direct air capture require thermal energy and large volume air movement from air cooling. Do you see a foreseeable future? Does this make any sense? This is a little out of field, out of scope, but it's a pretty interesting question.
I know less about direct air capture, but I do know that data centers operators have thought about how to use waste heat in various ways, including like trying to heat buildings or water supplies for heating. So I mean, say it's possible. Yeah.
Yeah, I think this would be very interesting to do. Like we have like so often in our computer chips like operating, like heat is a problem. But then even like David and I had also just submitted a recent proposal with Elsie Sunderland in the environmental chemistry lab, looking at these sort of forever chemicals that come out of the waste of semiconductor manufacturing. These like per and polyfluoroalkyl substances that get sort of dumped into the water. And one way of breaking those down is by heating them up to like a very hot temperature. But it's not, very cost effective to do that because you have to generate all that heat. But if you have some heat coming from something else, then it seems like you should be able to use that to, kill two birds with one stone.
We've had, and again, this is on the operation. Well, actually, probably this is on both, but this is on the operational side. So, if we think about improvements in algorithmic efficiency and improvements in chip speed and so forth, this raises this question of a couple of audience members have raised this question of what's called the Jevons paradox, which is as technology improves, you end up using more of it because it's cheaper. So, that goes back to steam engines becoming more efficient. And so we use a lot more coal. So the demand for coal actually goes up as the steam engine technology improves. What's that mean for these projections? I was really struck, David, by the wide range in your projections for energy demand for computing over the coming decade.
I feel like a lot of this comes down to economics and the business use cases for artificial intelligence. And if it's as transformative as people are saying, then maybe it'll be at that high end. And maybe if it starts to disappoint people and we see a little bit of the froth cooling off, then we'll probably be closer to the lower end of those projections. So it's really hard for anyone to make those projections. That's basically why there's such a wide range. We don't know. But really it's going to come down to all of computing is about, how does it help society? How does it improve productivity? And that varies out on how much AI will facilitate.
But yeah, I don't know. We get this, I get this Jevons paradox question often, and I just don't know what the answer is. Like I still feel compelled to keep making stuff more efficient. But I realize that then it ends up, having a bigger footprint overall. I don't know what to do.
Yeah.
Yeah, but it's a great thing to keep in mind and to think about. So Gage, going back to the embodied carbon, it's pretty easy to see, at least in some ways, an alignment on the operational side between energy efficiency, which just saves money to the operators, and reducing carbon footprints. They're not the same thing, but they're not unrelated either, because it depends on where you produce. But on the embodied carbon side, if you had a carbon tax, then that all of that electricity that you're purchasing would be part of how expensive the chip is, and then there'd be an incentive to use the low carbon designs that you've been discussing. But if you don't have that, what's motivating the market? What's motivating producers? What's motivating purchasers to actually pay attention to this embodied carbon?
Right. Yeah, that's a great question. And I don't know the answer really, which is why we've sort of been going down that first route of trying to have that be either some kind of related to policy or have some kind of taxes or sort of business side incentives on this. So like as part of this, one of these NSF expeditions projects that David alluded to, we do have like people on that team that are specifically looking at the sort of economics and policy side that don't have expertise on the computing side in the same way that we don't have expertise on that side. So I really do think that that is, at the end of the day, it's going to have to come down to something like that.
Yeah, I would say that's, of course, a carbon tax on all power and so forth is something that's actually in place in some places, like they have a price on carbon in the EU. It's something that may or may not persist in Canada. It's something that we don't have in the United States, so that varies from one location to another. But at least one way to think about the work that you're doing is that it shines a light on the magnitude of this, and so it's one more reason to start thinking about those policy interventions. But certainly, the measurement and the modeling is, an important scientific, an important step in and of its own right. So let me see. Oh yeah, a question. You mentioned this. I think maybe David, you mentioned this. I can't remember which one of you mentioned this in passing, but we did have a question about the water footprint. And so maybe because somebody could just say a little bit more about that.
Yeah, I can talk about that. So the report that I cited that had electrical projections also has projections for the water consumption of data centers, and the water consumption is quite high, and it's quite interesting because it's often a trade-off between carbon and water. The reason that data centers use water is because they don't want to use direct cooling, so they don't want to have air conditioning inside the data center. So they're using evaporative cooling, using a lot of water that's kind of flowing through. And so if you use more water, you use less electricity, and conversely, you can, instead use cracks and get the water usage down. It's quite high, and it's just another resource that needs to be accounted for when you're doing data center site selection. So, maybe Arizona isn't the best place if you're considering the water usage, and in addition to the solar panels you might have there.
That's really.
There's been proposals of like building data centers like underwater at the bottom of the ocean, right?
Yeah.
For some of these like additional cooling benefits or in rivers, to get water flow.
Yeah, this is all of this stuff is pretty impressively science fiction. Maybe I'll just leave it in terms of the audience questions, I'll leave it at that and see if you have any final words or final thoughts, things you think we've missed that you want to share.
I mean, I think there's a lot of interest in this area. It's been working in computer engineering for 25 years, and the last few years with the interest in AI, the CHIPS Act, and semiconductor design, it's sort of a golden age for thinking about these topics. So it's great to see the interest on this forum, and hope that there are people out there that are excited about the solution space and trying to take some of these academic ideas and push them into practice and get tangible benefits to society. That's ultimately what we're hoping to do with our research.
Yeah, I mean, same here. I feel like it's a great area to research because everybody realizes it's a problem. Many people are working on it and along completely orthogonal axes. We don't know what the solution is. And at the same time, there's a lot of the students, like the undergrads and the PhD students are just very passionate about this, that I just learn a lot of it like through them. like one of our, like I mentioned this PFAS project, like I knew nothing about PFAS. Like our student, Miriam, David and I work with, is like, hey, like we should look like beyond carbon footprint. Like there's this PFAS that's just horrible waste coming from these fabs. And I was like, what's PFAS? And now like that's another thing that we're working on. And so it's really cool to see the next generation driving a lot of this research.
And it's really great from my perspective to see the two of you and other scholars, other researchers, the postdocs and graduate students at Harvard creating this community around this problem and creating this, you know, the scientific understanding of the magnitudes. I think that's really cool. So thanks so much, Gage, and thanks so much, David. This has been really fascinating, and I'm really glad you took some time to join us. And thank you to the audience. Thank you for attending. Thank you to the people who helped produce and to the Harvard Alumni Association who helped to promote this. And we look forward to seeing you next month for another panel in Harvard Voices on Climate Change.